Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over how to find the extrema using the first derivative test. Now let's go ahead and take a look at the instructions for the example that we're going to be doing. We're to find and describe the local extrema. Okay, another word for local extrema are your relative extrema. Okay, so find and describe the local extrema. When we're talking about extrema, we're looking at the minima and the maxima. Okay, so we have to find and describe the local extrema using the first derivative test. Okay, there is another test that can be used to find and describe your extrema known as the second derivative test. We're going to be taking a look at that in later presentations. In this one, we're just going to focus on the use of the first derivative test, considering how the sign of the first derivative impacts the behavior of the function, and then using that to identify or locate our relative extrema. The function under consideration is f of x equals 5/3 x to the third power minus 20x. Now, in this problem, we are asked to find the extrema, local extrema. Anytime you see a problem involving extrema, you want to use a mnemonic device to help you recollect the procedures involved in the problem solving process. So anytime you're dealing with extrema, you want to remember CVS, okay, like the store that you go to, CVS. Now, what's the meaning of CVS? CVS basically tells you that when you are finding the extrema, you start by looking for the critical values, okay? Critical values, and then you'll also consider the endpoints. This comes to play when you are given an interval in which you have to find the extrema, the local extrema. And then after you find your critical values and you've identified your endpoints, you're then going to create a sign chart that will help you use the first derivative test to describe the behavior of the function using the sign of the first derivative. And then you also consider what happens around the endpoints. Okay? Alright, so let's go ahead and use the CVS process for this problem. Now, one thing you want to note is that no interval is provided here. So what are the endpoints? There are none. Okay? So for this problem, we're just going to look for the critical values and then use those to create our sign chart and then proceed from there. So let's go ahead and start. So step number one is what? Step one is to find the critical values. Okay, find the critical values. Now, how do you find the critical values? You find the critical values by finding where the derivative, where f prime of 0, when f prime of x is equal to 0, or f prime of x does not exist. Okay? When f prime of x equals 0, we have a horizontal tangent line situation. When f prime does not exist, we either have a corner, a cusp, a vertical tangent, or a discontinuity. Okay, so if you're thinking about extrema, most likely corners or cusps are the scenarios where you have an extrema. In other cases, it's a little bit complicated. Okay, now let's go ahead and find the first derivative of the function. So the function is 5/3 x to the third, so 5/3 x to the third minus 20x. Okay, so we will start by finding the derivative. So f prime of x, we're going to be applying the power rule in differentiating these two terms. So we have 5/3 times, you power this exponent down, and then you subtract 1 from it, minus the derivative of 20x is just 20, but let me show you the steps. So the power here is 1, you power that down, and then you subtract 1 from it. Okay, so let's simplify this equation right here, this function. So we'll have the 3's dividing out, and we have 5x to the 3 minus 1 is 2, minus 20. Now we will have x raised to the 0th power, which is just 1. So 20 times 1 is just 20. So we now have our first derivative. Now after finding your first derivative, it's beneficial to express it as a fraction. Okay? In this case we have a polynomial, but let me express it as a fraction. I'll divide it by what? By 1. So we are going to find out where f prime of x is equal to 0 and where it does not exist. Now let's think about this for a second. Well, I'll talk about that later. Let's look for f prime of x equals 0 first, okay? So whenever you're looking for f prime of x equals 0 and you have a rational expression, I just expressed this as a fraction to illustrate that point, you basically extract the numerator component of your first derivative and you set it equal to 0. Okay, so you set the numerator equal to 0 because when the numerator has a value of 0, then the entire function has a value of 0, assuming that the denominator does not have a value of 0 at that point. Okay, so let's do that. You take 5x squared minus 20, set that equal to 0, and we'll just solve. So we have a quadratic equation here, and we can solve this by isolating x using the square root property. So let's start. We can add 20 to both sides, so you have 5x squared equals 20. Divide both sides by 5, you have x squared equals 4. Then you take the square root of both sides, and you're left with x equals, don't forget, plus or minus, okay, plus or minus 2. Those are your critical values when we have a horizontal tangent or when f prime is equal to 0. Now, the second case we need to solve is where f prime does not exist. Okay? In this part, we are going to set the denominator to 0 and solve. Before we do that, let's take a look at this function. What kind of function is this? This is a cubic polynomial. Okay? A cubic binomial. It's a polynomial function. And what do we know about polynomial functions? All polynomial functions are smooth and continuous. Basically, all polynomial functions are differentiable everywhere in your domain. Okay, so there isn't any corner cusps, vertical tangents, or discontinuities of any nature for polynomial functions. Okay, so polynomial functions are always differentiable. So if you take a look at this question, when does the derivative not exist? Since this is a polynomial, we can clearly see that there isn't any x value that results in the derivative not existing. Okay, so let's just confirm that. We found the derivative. Now what we're going to do is set the denominator, which is 1, to 0. Okay, because anytime a function has a 0 value in the denominator, the output of that function is undefined. So if the denominator of this derivative function could attain a value of 0 at any point in the domain, then at that particular x value, the derivative will not exist. Okay, so take a look at this. When is 1 equal to 0? Never. So that clearly shows us that this function is differentiable everywhere in the domain, and there isn't an x value where f prime does not exist. Our conclusion, we have only two critical values, and they are x equals -2 and x equals 2. In some other problems involving rational functions, you might have a variable here, or you should have a variable in the denominator, and then that will help you find where the first derivative does not exist. And those ones qualify as critical values too. Okay, now another word for critical values are your potential extrema. Okay, these are like candidates to become an extrema. We do not know for sure if they are extremas yet. In order to get confirmation, we have to subject them to tests, either the first or the second derivative tests. In this particular problem, we are focusing on the first derivative test. Okay, so steps. We have executed the CV step. We found the critical values. Now the next thing to do is to create your sign chart. Okay, so let's go ahead and do that. So what we'll do is basically create a number line using our critical values. So there goes our number line, and then just graph the critical values on there. Let's put -2 and 2. Okay, now this critical values divides the number line into 3 areas. So we have, this is 1 and 2. Okay, so let's label it. This is we have 3 regions here. We have region 1, 2, and 3. What we're going to use this sign chart to do is to draw a connection between the sign of f prime and the behavior of f. Okay, when you're drawing that connection, what you're basically doing is using components of the first derivative test. Okay, so now what we're going to do is we're going to pick easy to use x values in each interval, determine the sign of the first derivative in that interval, describe the behavior of f, then we'll be able to easily see what our extremas are. Alright? Okay, so let's start with interval 1. What x value is easy to work with here? We can use, how about we use x equals 3. Okay, you don't want to pick a number that's difficult to use. You'll basically be making your life hard unnecessarily. So we're going to be using x equals 3 for the first interval. Second interval, x equals 0 is very easy. And then for the third interval, x equals 3. Okay, interval 1, 3 is not smaller than -2. Sorry about that, -3, that's what I meant to say. Okay, so -3, 0, and 3 are the numbers that we're going to be using to determine the sign of the first derivative in these 3 intervals. Remember, what we care about is just the sign, not the magnitude of the number. Okay, so let's go ahead and determine the signs. Let's start with interval number 1. So for interval 1, we're going to be using x equals -3. So the question is, what function are we plugging this into? Are we plugging x into the function or the derivative? Well, we are plugging it into the derivative because we want to use the sign of the first derivative to determine the behavior of the function. Okay, so we are going to be looking for f prime of -3. Okay, let's rewrite what f prime of x is. F prime of x, if you have forgotten, which I have, is 5x squared minus 20. So f prime of x is 5x squared minus 20. So we're going to be plugging in these values into that function. So when x is negative 3, we have, what do we have? 5 times negative 3 square minus 20. 5 times negative 3 squared is 9, right? So 5 times 9 is 45. 45 minus 20. Now, all I care about is the sign. 45 minus 20 is going to give us a positive result. Okay, so in interval 1, f prime is positive. Okay, what do we do next? We go to interval 2. Interval 2, we are going to use x equals 0 to determine the sign of f prime. So we're going to be looking at f prime of 0, which is 5 times 0 square minus 20. Okay, simplify that. 0 squared is 0 times 5, 0 minus 20. The end result is a negative number. Okay, remember all we care about is the sign. So we have negative there. Last interval, interval number 3. In that interval, we selected x equals 3 for a test value. So we want to determine the sign of the first derivative at x equals 3. So we plug in 3 into the derivative function, 5x squared minus 20, which gives us this expression right here. So 3 squared is 9 times 5, which is 45, minus 20. Our answer here is positive again. Okay? So we have positive, negative, positive. Now just a side point, the alternation of signs here doesn't always happen. Sometimes you have two identical signs next to each other. So don't think that if this is minus and plus, then the other has to automatically become a minus. The signs do not always alternate. It just so happens in this particular problem. Okay, now let's go ahead and use the signs that we just determined for f prime to describe the behavior of f. So when f prime is positive, our function is going to be increasing. Okay, increasing means you're going up from left to right. F prime is negative here, so that means that our function is going to be doing what? Decreasing from left to right. Our function is, the first derivative is positive here, which means that our function is going to be increasing from left to right. So if you look at this behavior, can you determine what the local extremas are? Using the first derivative test, we have a local or relative maximum here because the first derivative changes from positive to negative, or the function goes from increasing to decreasing, so we have a local max. And at x equals 2, we have a local minimum because the first derivative changes from negative to positive, or the function goes from decreasing to increasing. Okay? Alright, so let's go ahead and write down our answers. So we have two extrema in this problem. Our extrema are the combination of our minima and maxima. So our extrema is x equals negative 2 and 2. Now we need to describe them. What are they? Which is the max, which is the min? Okay, so we have a local maximum or relative maximum at x equals negative 2. We have to provide justification using the first derivative test. So we have a local max at x equals negative 2. And this is because if the first derivative f prime changes from positive to negative, if f prime changes from positive to negative, then f changes from what? Changes from increasing to decreasing. which results in what? According to the first derivative test, which results in a local or relative maximum. Okay, because you're going, think about a roller coaster. You're facing up, you're heading towards the sky, and then you're going down. At the point where that switch happens, you have a maximum. Okay, so that's basically the justification as to why we have a local maximum at x equals -2. All right, so let's go ahead and identify our next extrema. We have a local minimum at x equals what? At x equals 2, because providing justification, if f prime, the first derivative, changes from negative to positive, if it changes from negative to positive, then f changes from what? If you're going from positive to negative to positive, f is going to change from is going to change from decreasing. A negative derivative means that you have a decreasing slope of a tangent line, which means the function is decreasing, to increasing. Okay, when the first derivative is positive, the function is increasing. So if you have this change in the function from decreasing to increasing, this results in results in a local minimum. All right. So when you're taking the AP exam, a lot of times they'll ask you to identify the extrema and provide justification. All you just have to do is state what the first derivative test is, or if you're using the second derivative test, just write what it is within the context of the problem. Okay, so this is basically what your this is what your extrema are, and then this is a justification as to why they have the description that we gave to them here. Okay, so that's that. Thank you so much for taking the time to watch this presentation. Really appreciate it. If you found the contents of this tutorial helpful in your study of the applications of derivatives, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions about what we covered in this presentation or any comments, just place it in the comment section below, and we'll be more than glad to respond. Don't forget to subscribe to our channel for updates to other cool calculus tutorials such as this. More clips can be found on math.serve.com underneath AP Calculus. Thanks again for watching, and have a wonderful day. Goodbye.